I'd like to talk about a misunderstanding that I've had for a very long time, and I think that I might not be alone. So I'd like to bring the misunderstanding out into the open and talk about some of the consequences of the misunderstanding. In this discussion, I'm going to make some assumptions about some variables. None of these assumptions should be taken too seriously. If they turn out not to be strictly true, it doesn't hurt the argument very much, but here they are. All the variables I'm talking about are going to be normally distributed, and they're going to exhibit multivariate normality, which essentially means that they're normal and they have linear relationships only. Nothing fancy. No interactions, no quadratic effects, no polynomial effects, no multiplicative anything. They're just linear effects. I'm also going to assume that the correlations that I present are population parameters, and that there's no error in estimating them. These assumptions are probably false in every way, except that they're not that false. They do a pretty good job of capturing reality most of the time. A learning disability, as it's traditionally defined, involves ruling out a number of conditions, such as low intelligence, poor teaching, extreme cultural differences that make it difficult to learn in a particular setting, sensory and physical disabilities that make it difficult to learn. A learning disability is defined by having generally intact cognitive abilities, but specific cognitive weaknesses, cognitive processing deficits, that explain the academic weakness. That is, there's some academic domain, let's say we have reading decoding. This particular person has a reading decoding score of 75. An index score of 75 corresponds to the bottom 5th percentile. We would need to measure more abilities than just GC, but let's say this person has a 100 GC. GC means understanding of language and broad knowledge. A score of 100 would be an average score. Phonological awareness is the ability to hear phonemes in sounds distinctly. People who have difficulty hearing sounds within words distinctly have difficulty understanding how the sounds correspond to letters, and it makes it difficult to read. This person has a 75 phonological awareness, also at the bottom 5 percentile. So the difference between GC and phonological awareness is 25 points. Almost certainly this is a statistically significant difference, and it's also probably a rare occurrence for someone to have that large of a difference. GC would be considered a cognitive strength for this person, and phonological awareness would be a cognitive weakness. The difference between the cognitive strength and the academic deficit is also 25, and the difference between phonological awareness, the cognitive weakness, and reading decoding is 0. For most of my academic career, if I saw a pattern like this, I would think that pretty much my job is done. That phonological awareness is theoretically related to reading decoding, is much lower than GC, and is consistent with reading decoding. That essentially I've got a pretty good explanation. I've come to understand that this conceptualization is incorrect. Well, not exactly incorrect, but very incomplete. There's a kernel of truth to it, but much more needs to be understood than just this. Unfortunately, in order for me to tell a more complete story, I have to put up a kind of scary diagram. Here it goes. Alright. So this may look intimidating at first, but I promise that if you don't understand this figure, it doesn't diminish your understanding of my overall point. And I think that you will be able to understand the diagram if we take it slow, point by point. This is a multiple regression model. In multiple regression, we measure a bunch of variables for a lot of different people. In this case, I have 3 variables. Again, GC, phonological awareness, and reading decoding. So if we collect a lot of data from a lot of people, and then we calculate the correlations between these 3 things, we can make an equation, a prediction equation. And what we do with the prediction equation is that we look at the predicted value for a particular individual, in this case 100 for GC and 75, and then we make a forecast as to what their reading decoding score is going to be. Now we already know what their reading decoding score is, so what's the point of making a forecast? The point of making a forecast when we already know the outcome is that we can see how the person compares to other people with these 2 scores. That is, in the population, if someone got a GC of 100 and a phonological awareness of 75, what do most people do, and how far off is this person from expectations? So prediction in this case is a bit of a misleading term. We're not really forecasting. What we're doing is we're checking how well someone is doing compared to expectations. So here are my 2 predictors. These 2 predictors are correlated. The correlation is symbolized by this curved double-headed arrow. The correlation can be symbolized with this R, and then the subscript is what is the correlation between. So R with subscript gc.pa means the correlation between GC and phonological awareness. This straight arrow represents the effect of GC on reading decoding. Now when I say effect, I mean something loose. It doesn't have to be a causal effect, but we're using it in a predictive sense. This arrow could have been drawn straight all the way from GC to reading decoding. In fact, that's the way it's usually done. But I've put in an intervening step because I think it's important. So this effect is going to this box here, y hat, which I'll explain in a moment. But this slope means what is the relationship between GC and reading decoding if everyone had the exact same phonological awareness score. So it's a fiction. Let's pretend that everyone had the same score for phonological awareness. If that were the case, what would the relationship between GC and reading decoding be? Likewise, this B2 is the relationship between phonological awareness and reading decoding if everyone had the same GC score. They don't, but let's pretend that they did. This triangle represents constant 1, and we're going to take that constant and multiply it by the intercept. The intercept means the same thing that it meant in your Algebra 1 class. What is the score of y when your two predictor variables equal 0? Now in this case, no one ever has a score of 0 of GC and phonological awareness. But if they did, what would the predicted score of reading decoding be in that case? And that is the intercept. So we have an equation. It's reading decoding equals the intercept here plus the slope for GC times the particular score of GC for an individual plus the slope for phonological awareness, B2, times the score for phonological awareness, plus error. What is error? In this diagram, error represents the portion of reading decoding that is not predicted by these two predictors. That is, these two predictors will give us some information as to what the reading decoding score is going to be, or likely to be, but we're not going to hit bullseyes every time. We're going to be off by a certain amount. That certain amount is called an error. I prefer actually the term residual because error makes it seem like there was a mistake made. It's no mistake. And we're not talking about measurement error. What we're talking about is the inability of these two predictors to predict reading decoding exactly right. And so residual is that which is left over, but we can use the term error. This thing in the middle, y hat, it's a y with a caret on top. Y hat is the predicted value of y is reading decoding in this case, for a particular combination of these two scores. These three scores have a mean of 100 and a standard deviation of 15. This notation may seem a little confusing at first, but let's take it apart. GC followed by a tilde means distributed as, and then the italicized n means normal. So it means GC has a normal distribution. Normal distributions have two features. They have a mean and they have variance. The mean is the first number, so this means a normal distribution with a mean of 100 and a variance of 225 or 15 squared. The square root of variance is the standard deviation. So put it together, we have GC as a normal distribution with a mean of 100, standard deviation of 15 or a variance of 225. This is the familiar IQ metric or the index score metric. Phonological awareness and reading decoding also have an index score metric. The predicted score y also has a certain distribution. Y hat has a normal distribution also with a mean of 100, but its variance is not 225. The standard deviation is not 15 squared. It is 15 times the multiple correlation squared. Now what is this multiple correlation? The multiple correlation is the correlation between the predicted score and the actual observed score, reading decoding. What multiple regression does is it finds the optimal combination of this intercept and these two slopes such that the correlation between y hat and y is maximized. How that's done involves some fancy math called matrix algebra. We're not going to get into that. But suffice it to say that multiple regression finds the best combination of these three numbers such that this correlation becomes as big as it can be. Unfortunately, in most cases, the multiple R is not perfect, that there's going to be some part left over, and that's the error. The error term is the portion of reading decoding that is not accounted for by GC and phonological awareness. It has a certain distribution. We're going to assume that it's also normal. It has a mean of 0, and in this case, it has a variance of 15 squared times 1 minus the multiple R squared. To estimate all of these numbers, we're going to need a set of correlations. For inspiration, let's take the correlations from the Woodcock-Johnson 3 normative update for ages 9 to 13. In this case, reading decoding is the basic reading skills composite, and phonological awareness is the phonemic awareness 3 composite, and GC, of course, is just GC. Using these correlations and these means and standard deviations, we can estimate what the slopes and the intercept are. So the multiple R squared is 0.4, which means that 40% of the variance in reading decoding has been explained by these two predictors. Reading decoding for this individual is 75, the intercept is 31.55, here it is. The slope for GC is 0.240. For this individual, GC is 100. The slope for PA is 0.264 here. And this individual has a 75 in PA. If we know all of this information, we can solve for how much error there is. All of these numbers, if we solve for all of them, it comes out to y hat. The predicted value for reading decoding is 93.4. That is, approximately half of all people score this or higher, or this or lower. This is the dividing point. This individual scored 75 on reading decoding. That is, 18.4 points below expectations. We can estimate how rare this is given some properties of the normal curve. So as I said, 40% of the variance in reading decoding has been explained. This dark green distribution is the normal distribution for the whole population when reading decoding has a mean of 100 and a standard deviation of 15. If we know that GC is 100 and phonological awareness is 75, we can estimate what the scores are going to be, what the distribution is going to be, and it looks like this. In the whole distribution, 95% of the scores fall between these two lines, approximately 70 to 130, a little less. The width of the 95% confidence interval is 59 points, approximately 4 standard deviations wide. If we happen to know the score for GC and PA, the 95% confidence interval is narrower, but not a lot narrower. So the mean of the whole population in reading decoding is 100. That subset of people who have GC equals 100 and phonological awareness of 75, that subset has a mean of 93.4 and the standard deviation is 11.64. That is, this light green distribution is the distribution of scores for this subset of people who happen to have these predictors. Their reading decoding scores are not all the same, but they have a normal distribution. That normal distribution is about 6.6 points, about a half a standard deviation, a little less, from the population mean. 95% of these scores fall from about 70 to about 116. The width of this confidence interval is 46 points, a little over 3 standard deviations. So instead of a 4 standard deviation width of the confidence interval, we have about 3 standard deviations. That is, our 95% confidence interval no longer contains this range from about 116 to about 130. So when we've explained 40% of the variance, it's not a lot. Is it useful? Yes, of course it is. But is it precise? Well, we're not getting precise predictions. If reading decoding for this individual is 75, you can see that it's unusual in both distributions. It's more unusual in the whole population and a little less unusual in this subset, but it is unusual in both populations. Let's see how much exactly. So we're going to take this normal distribution and turn it on its side. On the x-axis we have the predicted reading decoding scores, and on the y-axis we have the obtained reading decoding scores. If we imagine the whole population of people for whom their predicted reading decoding scores is 93.4, on average, their obtained reading decoding scores are 93.4. But they're not all equal to that. They cover a full range, and the standard deviation is 11.64. This cutoff score here represents an obtained reading decoding score of 75, and using the properties of the normal curve, we can estimate what proportion of these people who score GC equals 100 and PA equals 75 have a reading decoding score of 75 or less. Using the properties of the normal curve, we can estimate that about 5.7% of people with these predictors have reading decoding scores of 75 or lower. So this individual who has a reading decoding score of 75 is actually somewhat unusual, even though phonological awareness is 75. So let's contrast this distribution with the distribution of people who have 100 for both GC and phonological awareness. That is, there's no cognitive deficit. If this is the case, the predicted score for reading decoding is also 100. But not everyone with 100 GC and 100 PA have reading decoding of 100. There's variability in this subgroup. Some people will score as low as 75 or lower. About 1.6% of kids with 100 GC and 100 PA will have reading decoding scores of 75 or less. That is, it is even more unusual in this distribution to have 75 or lower. Let's take a look at both distributions. When you have 100 GC and 75 PA, there's a 5.7% chance that a person has a reading decoding score of 75 or less. In this distribution, when you have no cognitive weakness, there's a 1.6% chance of scoring 75 or less. They're unusual in both distributions, but it is about 3.6 times more likely in the distribution when PA equals 75. This ratio is called relative risk. So the relative risk of scoring 75 or less is 3.6 times greater when a person has a cognitive weakness compared to no cognitive weakness. Now this relative risk depends on how severe is the cutoff point for what we call low performance. In this regression model, we can look at what the relative risk would be at various points on the reading decoding scale. So we're comparing two profiles, one in which there's a cognitive weakness, PA equals 75, and one in which 100 is the score for both predictors. If 100 is the average on reading decoding, it looks like there's a 1.5 relative risk of scoring less than 100 in this profile compared to that profile. If we go down to 90, which is the cutoff usually for the average range, it looks like there's about a double chance of scoring less than 90 if you have this cognitive weakness. There's about a triple risk if it looks like around 78 or 9. And then for 75, we had that 3.6. The further down we go for the threshold of what we call low scores, the relative risk gets higher and higher for this profile compared to this profile. So it is true if you have a specific cognitive weakness that's relevant to the outcome that you're more likely to have a low score. But in many cases, it's simply a risk. It is not an explanation. We can ask, if GC equals 100, how low does phonological awareness have to be before we have a good explanation of the fact that reading decoding is 75? So here's our distribution. The predicted score for this distribution is 75. That is, on average, these people have a reading decoding score of 75. This distribution has a mean of 75 and a standard deviation of 11.64. In order for this to happen, if GC equals 100, then phonological awareness has to equal 6. In this distribution, half of the scores are lower than 75 and half are above 75. That is, PA must be less than 6 before it is typical for a person with GC equals 100 to have a reading decoding score of 75 or less. Now, on the index scale, how low is a score of 6? Well, it turns out that about 1.2 people in the world would be expected to have a score of 6 or lower on any particular perfectly normal distribution. That is, it is extraordinarily unlikely for someone to have a score this low. And we certainly wouldn't be able to observe a whole population of these people because, well, there's probably only one person in the world with a score this low. Of course, this assumes that we're dealing with a perfectly normal distribution, and as I said, most of these things do not have perfectly normal distributions. My point is that in order for us to say, of course you have a reading decoding score of 75, it's totally typical for you, we would have to have this particular profile of predictors, which is extraordinarily unlikely. And therefore, we just don't have conditions in which it's typical for people to have reading decoding scores of 75 given these predictors. Now, I hear you saying, of course, crystallized intelligence and phonological awareness are important predictors, but they're not the only predictors. There are more predictors. And of course there are. So let's take more cognitive predictors. So we have CHC abilities, crystallized intelligence, fluid intelligence, visual spatial processing, auditory processing, of which phonological awareness is a part, long-term storage and retrieval, short-term memory, including working memory, and processing speed. So imagine that we had, again, Woodcock-Johnson 3 normative update scores for all 7 of these cognitive abilities. And let's say we have 2 different people. One of these people has an index score of 100 for all 7 predictors. Another person has average scores for what most people consider the core of intelligence, and then low scores, 75, for the remaining scores. That is, we have lots of processing deficits and then some cognitive strengths. Now the question is, how typical is it for a person with this profile to have a reading decoding score of 75 or less, and then how typical is it for a person with this profile to have a reading decoding score of 75 or less? Well, the distribution of reading decoding for a person with this profile would be a mean of 100, standard deviation of 11.24, and the risk is 1.3%. That is 1.3% of people with this profile, 100s across the board on the Woodcock-Johnson, would have a reading decoding score or basic reading skills score of 75 or less. 1.3%. Doesn't happen very often. Well, what about this profile? Well, on average, these people have a reading decoding score of 90.5. By the way, 90.5, that's still considered in the average range. So half of people with this profile would be predicted to have a reading decoding score of average or better. And of all the people with this particular profile, 8.4% of them would have reading decoding scores of 75. 8.4, that's not a lot. Most people do not have reading scores this low, even with this pretty severe profile. The relative risk is higher than it was with just 2 predictors. The relative risk is now 6.4. That is, it's 6.4 times more likely to have a person with a reading decoding score of 75 or lower with this profile, this LD-looking profile, compared to this no cognitive deficit profile. In this scenario, what percentage of the variance have we explained when we use 7 cognitive predictors? Well, it rose from about 40% of the variance with 2 predictors to about 45% of the variance with 7. Most of that, by the way, comes from working memory. So even with all 7 predictors, we are not explaining more than half of the variance, which means that there are a lot of other influences on reading decoding. And thank goodness, because that means that there's room for intervention to work. If we had information on these other variables that might matter for reading decoding, we could put them in a regression equation, but often we do not have access to those sorts of equations. So what are we to do? Well, I have a conclusion. First, we have to abandon dichotomous thinking. In my example, phonological awareness does matter, but the question isn't whether it matters, but how much. Often, as we saw here, the predictor was relevant, but it was a risk factor, not a sufficient explanation. Should we add more cognitive predictors? Yes. Will that improve our ability to explain things? Yes, it will. But we should remember that often it can only take us so far. What we can't say is, I know why you're having trouble. It's because of your cognitive profile. I get it now. No, that's not typical. Unless, of course, the person has low cognitive ability across the board. But when we're talking about a case of learning disability where we have generally intact cognitive abilities, rarely can we say, this narrow ability is what's causing the problem. No, the narrow cognitive ability that is low is usually only a risk factor, not a full explanation. And we have to look a little bit deeper if we're going to serve our clients well. So I have some recommendations. First, we definitely should use the best available data and models, and we can use complex ones. Here's a model that you can't really see here, but it's from my program, the Compositator, and with it you can do some fancy stuff. But even I who love fancy models, I have to recognize that it only takes me part of the way there. And like any good clinician, and like you've been doing all this time, you have to do a whole lot more. We have to look at the development of the person, their learning history, their current context, and then combine these 2 sources of information, the learning history, the stuff you get from a really good interview. These narrative explanations and the statistical explanations need to coexist, need to be bound together, need to have a sort of dynamic tension. That is, these 2 kinds of clinical activities, the storytelling, narrative explanation, needs to be anchored in the best available data. And the best available data needs to be anchored in clinical judgment, of course. And these things exist in a sort of dynamic tension. Hence the little spring coil. That's my attempt to show dynamic tension. But what I'm getting at here is a kind of ambitiousness with a narrative explanation and a statistical model, but also a humility about the limits of what we can do, and full disclosure to the people that we serve. That we have some ideas as to why the trouble started, we have some ideas as to what needs to be fixed and how to do it, but in the end we all see through a glass darkly. So that's my error. Now that I've gotten it off my chest, I've confessed my crime, my sin, my weakness. I hope that I will have helped someone else who may have been in the same boat.